So in the previous section, I got you to try out some problems related to work and kinetic energy, hoping that you may notice something, and that something is called the work kinetic energy principle. So that's the topic for today, and what I was hoping you would notice is basically the formula down at the bottom left here. I had you calculate the kinetic energy of an object before any forces acted on it, and then calculate the net work done on the object by all the forces acting on it, and then calculate the kinetic energy after all of the forces acting on it. And hopefully you found that when you add the starting kinetic energy with all of the work that's done on it, that the total equals the amount of kinetic energy that the object had afterwards. So basically, what I'm trying to say is that when a force does work on an object, it's going to affect its kinetic energy. So kinetic energy is measured in joules, and work is also measured in joules. So another way of saying this is that if an object starts off with so many joules of kinetic energy, then you do work on that object, that's either going to add joules or take away joules from that object, and you result in the ending amount of joules in kinetic energy. I say add or take away because we know that work is sometimes positive and work is sometimes negative, and work is sometimes zero as well. So another way to rewrite this, if I were to take the K1 and I would subtract K1 from both sides, it would end up as net work equals K2 minus K1. And whenever you have final minus initial, that can be rewritten as a delta. So on the right hand side here is another way to rewrite the same equation. And this is what's on the formula sheet actually, what's on the right hand side here. Okay, you can use either when you do a problem set or any homework or anything like that, but in terms of a formula sheet, what you would see on it is this one right here. So it says that the net work acting on an object, or sorry, the net work that's done on an object is equal to the change in the object's kinetic energy. The net work done on an object is equal to the change in the object's kinetic energy. And that's only true if the mass of the object remains constant. So a couple of, I guess, more straightforward questions. Number one, if an object has 50 joules of kinetic energy, and then 100 joules of work is done on it, what's the new kinetic energy? And the answer is simply just adding the two together. Okay, this is the starting amount of joules of kinetic energy, and then you add 100 joules of work. The principle I'm trying to teach you is that the joules done by work is just added on to the kinetic energy. All right, so the 50 joules of kinetic energy now becomes 150 joules of kinetic energy. And this is, these are just the steps shown from the formula that was on the left-hand side of the previous screen. I could also start with the formula from the right-hand side of the previous screen as well. Work net equals delta K, because that's on the formula sheet. So if I start with this, the first thing I would do is I would rewrite the delta K as K2 minus K1. Okay, delta anything can be rewritten as final minus initial. And then filling in the values, 100 joules was the work done. 50 joules was the starting kinetic energy. So then if I solve for K2, that would be adding 50 to both sides. I get 150 joule, the same answer. All right, then that's no surprise because these are the same formulas. As a second example, a 20 kilogram object's speed decreases from 8 meters per second to 6 meters per second. How much work was done on the object? So in this situation, I have to find the work. So now look, we have three ways to find work now. We have the work formula, force times distance times cosine of theta. We have that it's the area of a force versus displacement graph. And now we have a new way to calculate the net work done on an object. So that's all the works done by all the forces put together. And you can find the net work by calculating delta K. So once again, delta K is rewritten as K2 minus K1. And then K, kinetic energy, has its own formula, half mv squared. So I do that for the final speed and subtract the same thing for the starting speed. I would fill in all the numbers because I'm given the mass, given both of the speeds. So I fill them in. I'll end up with 360 minus 640 joules, and that equals negative 280 joules. I underlined the correct sig figs there, or decimal places in this case. So the net work done on this object was negative 280 joules, and it's perfectly okay for work to be negative. In this case, you may have noticed that the speed decreased. So does that have anything to do with why the answer for the net work is negative? And yes, it does. I'm going to explain that on this next slide here. So WKP, that's just going to be my short form for the work kinetic energy principle, which is this equation here, the work kinetic energy principle. And it's got a left side and it's got a right side, and they're equal to each other. So delta K is the change in kinetic energy. And you should know that kinetic energy is the energy associated with an object's motion. The faster something is, the more kinetic energy it has. The slower something is, the less kinetic energy it has. So if the left side is positive, so that's to say if positive net work is done, then the right side has to be positive. So that means the change in kinetic energy has to be positive. Well, that means it got more kinetic energy. That means it got more speed. Similarly, if the left side of the equation, so if the net work is negative, then the right side of the equation is negative, and that would mean that the change of kinetic energy is negative. So now there's less kinetic energy. That means the speed decreased. And finally, if the net work was 0, if it all added up to be 0, then the right side of the equation also has to be 0. And that would mean that there was no change in kinetic energy. No change in kinetic energy. That would mean that the speed stayed the same. Okay, so yeah, if it got faster, then the net work was positive. If it got slower, then the net work was negative. If it stayed at the same speed, then the net work is 0. So a couple of questions related to that. An object had an initial speed of v. Two forces act on the object over a displacement of 10 meters forward. So here are the two forces. The first force is a constant force of 50 newtons forward. And F2, the second force, does negative 400 joules of work on the object. At the end of the 10 meter forward's displacement, is the object's speed higher than v, lower than v, or equal to v? I already have the first step written out, actually. I meant to hide it, but oh well. So if we want to apply the new topic for today, the work kinetic energy principle, or WKP, then we have to calculate the net work. And to calculate the net work, we can add up the individual works. So my first step here was to find work 1, or the work done by the first force. In this case, I'm using the work formula. So it's force times displacement times cosine of theta. So that's 50 newtons times 10 meters times cosine of 0 degrees. 0 degrees because the angle between forwards and forwards is 0 degrees. They're in the same direction, the exact same direction. So the angle is 0 degrees. So that means it's 50 times 10 times 1, which is 500 joules. And then work 2 is already done for us. Okay, if you got to read these questions really carefully. So it says force 2 does negative 400 joules of work on the object. So I don't have to calculate anything. The work is already given to me. It's negative 400 joules. So I put the two of them together to get the net work. So it's positive 500 and negative 400. That results in positive 100 joules. So how is this helpful to answer my question? My question is, did the object's speed get higher or lower, or does it stay equal to v, what it was before? Well, we can say that since the net work we calculated was a positive number, since it's a positive number, that means that the kinetic energy increased by 100 joules. And if the kinetic energy increased, that means it got faster. So this is the work energy principle. One more one. This one is, I threw this in because people can get tricked because of the directions here. So if I explain this, hopefully you won't get tricked. An object's velocity changes from 10 meters per second east to 10 meters per second west. What net work was done on the object? An object's velocity changes from 10 meters per second east to 10 meters per second west. What net work is done on the object? So I can apply my new concept, the work energy principle. So the net work is equal to the change of kinetic energy. And I'll replace delta K with K2 minus K1. Now here's the important thing to note. The final speed is 10 meters per second. And the initial speed is also 10 meters per second. So they're equal. So if the speeds are equal, then the final and initial kinetic energies are equal as well. Because kinetic energy only depends on speed. It does not depend on the direction. So these east and west are actually just decoys in this question. It doesn't matter what direction they're going at. The answer to this question is going to be the same, in that the net work done is 0 joules. Because the final kinetic energy minus the starting kinetic energy is 0. All right. The speed probably changed in the middle somewhere, but the question is not really asking about what happened in the middle. It's just asking about the net work. So the answer here is 0 because the speeds were the same at the beginning and the end. So that's the work energy principle. There's a Google form for you to check your understanding on these. And then the next lesson, we'll have a few videos actually on different problems that you can solve. So they'll be longer with a lot more steps. This lesson here is just meant to go over this one concept.